As populations become more urban, air quality becomes an increasingly important aspect of daily life. When you think about a city with tens of millions of people and all the activities that they partake in, they have to transport themselves, we have to deliver goods to them, we have to provide power to them. All of these processes are based on combustion, still to this day. We're trying to move away from combustion, but as long as combustion drives daily life, emissions in cities will be a problem.
You know, when you burn coal or oil or natural gas, it's not just CO2 that comes out, but also these other gases, the NO2, the SO2. So we really want to understand both the atmospheric chemistry and the climate impacts of pollution.
Air quality has become an international public health issue. According to the World Health Organization, air pollution is linked to 7 million premature deaths every year. And not only air pollution, but also climate change or the impact of emissions on the ozone layer are other concerns that our society needs to address.
So the atmosphere is divided into layers, and the lowest layer, where most of our weather occurs, we call the troposphere. The second layer of the atmosphere we think about is called the stratosphere. And the stratosphere is really important because it has the ozone in it, and ozone is a really important gas for the Earth. It screens harmful ultraviolet radiation. That's the radiation that can give you sunburns, it can cause skin cancer, it can damage crops, it leads to cataracts in your eyes, so we care about the ozone layer a lot.
So, air pollution, the ozone layer, melting ice sheets and forest fires are all important issues that we need to understand in order to protect the population.
So there's a lot of stuff that comes up from the surface. So understanding the amounts that are getting up there, understanding what they're doing when they get up there, this is really important to know what's going to happen to both our ozone layer and climate in the future.
Answering these questions is an important task, and one that NASA has been working on for a long time.
The Earth Science Division that we have at NASA is part of the Science Mission Directorate. And as a division, what we do is we look at the Earth, significantly utilizing the vantage point of space to study the whole planet.
With what NASA does with Earth science, we try to understand the system as a whole, which means we try to observe the system from space, we observe the system from the ground, we observe the system from aircraft to try to best understand how the system works.
We are looking at the Earth system from so many different angles. We're looking at the carbon cycle, we're looking at air quality, we're looking at the cryosphere, we're looking at the amount of ice, we're looking at the oceans, sea level rise, looking at biological productivity of the land and the oceans.
Looking at long-term data records, that's very important because that tells us how the Earth system is changing. And so improving our ability to make measurements from satellites will give us a better long-term data record.
Satellites help us collect the data we need to study the Earth, but sometimes that's not enough.
Well, when we do measurements, we get them on different scales. So when we measure from a satellite, we tend to measure globally because that's how satellites do measure. They often will get us very detailed measurements, but not necessarily as a function of altitude that we would want to get, or they get the spatial coverage that you want to get. So sometimes they'll just sample along lines and we want to fill in the picture sideways or up and down, those types of questions. So sometimes we have to bring an airplane there in order to fill in the gaps.
And so if we can make highly calibrated, very good measurements from an airplane and compare those to the measurements from a satellite, we can improve our ability to make those measurements from a satellite.
Airborne research is therefore the perfect way to fill these gaps and help us gather more detailed information about the processes that take place in the atmosphere. But the Earth is a pretty big planet, with a circumference at the equator of 24,900 miles, or 40,000 kilometers. And the troposphere, the layer of the atmosphere we live in, which can range from sea level to over 33,000 feet, or 10 kilometers. So how could scientists study the Earth with multiple instruments that could cover large areas of our planet? Well, they needed a long-range, heavy-lift research aircraft that could carry large payloads of instruments, researchers, and fuel. And that's why, in 1985, NASA acquired a 4-engine airliner, the Douglas DC-8, which they modified for airborne research and put into service in 1987.
First off, the DC-8's an outstanding platform for airborne science. Structurally, it's a very robust airplane. The 4 engines allows it to perhaps go into places that you might be hesitant to with only a 2-engine airplane. The ability to put pylons on an airplane and probes on an airplane is a very unique thing. So the DC-8 has a lot of surface area you can do that with. Then it's the volume inside the cabin allows you to put multiple instruments on, and when you see a campaign, you'll see the airplane is full from nose to tail with instruments, and you'll have 20 some odd independent instruments on board with operators and unique requirements that they need to meet. So sometimes you're flying low for one instrument and high for another, and you have to figure out on a flight plan how to implement that and get them the data that is important to each of the different instruments.
The aircraft has a maximum flight duration of 12 hours and can operate up to an altitude of 42,000 feet. It can support a payload of up to 30,000 pounds and can seat up to 45 researchers and flight crew members.
It's large enough to put a comprehensive payload on and still fly a long distance so that you can do these, really extended sorties. I mean, when on the ATOM trip, we did one flight from Christchurch, New Zealand to Punta Arenas with a full load of comprehensive payload and all the spares and everything that we needed to operate. So that's the great thing about the DC-8. I mean, there's some other aircraft that may go a little higher, but it has a good altitude range, getting well into the stratosphere in a lot of parts of the world at 40,000 feet. But we're also able to fly down low, as we're doing on this mission a lot. 1,000 feet above the ground routinely, and then doing these missed approaches at airports where we get down to 100 or 50 feet off the ground. So that's really amazing that you can do all those things in one platform.
So the DC-8 is a fantastic platform for airborne research, and NASA used it regularly from 1987 until 2024, when it completed its last mission. But let's back up a bit. The 80s came with new ideas, music, style, and technology. But they also came with a growing concern about the thinning of the ozone layer that protects us from the sun's ultraviolet radiation, which was observed every year in the springtime. This led to an increase in atmospheric research, including one of the earliest campaigns of the DC-8 and ER-2 over Antarctica with the Airborne Antarctic Ozone Experiment in 1987. Results from this campaign confirmed the link between CFC-derived chlorine and the extremely rapid destruction of ozone. The impact of these discoveries at the time led to one of the greatest successes in communication between the scientific community and global political action, resulting in the so-called Montreal Protocol, which banned and controlled emissions of ozone-depleting substances.
At the time, the DC-8 had, as it does now, one of the world-class payloads for atmospheric chemistry, but it was mainly trace gas measurements. there were not a lot of aerosol measurements on the plane yet, the particles. It also had measurements that took some time to integrate, so 5, 10, 30 seconds, even a few minutes in some cases for some of the measurements. But at the time, that was more than sufficient. And at the time, we were mainly focusing our attention on the remote atmosphere, so the need to measure very, very quickly was somewhat mitigated by the environments that we were exploring. And we were just trying to understand how the atmospheric chemistry worked.
Early campaigns focused on understanding the interactions of different gases and particles, covering vast areas of the planet. And not just ozone-depleting substances, but also emerging concerns such as air pollution.
I graduated my PhD in '88, and I started flying with NASA in '91. On the DC-8 was the first trip that I ever took, and we came actually pretty close to here. We did the NASA PEM West mission, so we flew out of Hong Kong and Japan, Yokota Air Base in Japan, sort of looking at a large outflow of Asian pollution over the Pacific Ocean. But we've actually gone to a lot of different places all around the world. In the early days, we went to the Southern Pacific to try to find cleaner air, but it turns out that the big discovery on those campaigns, which was called PEM Tropics, was how pervasive the smoke from wildfires in South America and the Southern African continent. And they were just all over the Pacific Ocean, just flooded with biomass burning pollution everywhere we went. So that was a real surprise.
So as I mentioned, when we first got started with the DC-8, it was a great way to explore the world in the remote atmosphere. Do we see human impacts there? And the answer was yes. But also, do we have the ability to really measure the finest amounts of trace gases in the atmosphere? That early work was kind of seat of the pants, follow your nose, make these measurements. And it wasn't until the early 2000s that atmospheric modeling became mature enough to begin to guide what we do. And so a lot of our flights began to be built around model forecasts, and with the intent that you may or may not see what the model forecasted. So this idea of how to improve models by making measurements that really challenge the model is something that we started, more than a decade into using the DC-8, but to this very day, that's a very important part of what we do.
It was the improvement of atmospheric models and weather forecasting that allowed scientists to be more precise in their research and guide aircraft to the most valuable locations for sampling. At the same time, the more information they gathered, the better they could continue to improve those models. And not just the models, but it also helped calibrate another technology that was a game changer.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and liftoff.
It was about the same time, late 1990s, early 2000s, that satellites became an important part of what we were trying to do. And so prioritizing satellite observations, trying to fly in ways that would interact with the satellite observations, has been going on again for 20 years.
A new way of designing campaigns was implemented, like Arctis, in which satellites and airplanes worked together to gather information to understand how pollution was affecting the Arctic regions. Arctis involved 2 deployments, evaluating the difference between human-related emissions in the spring and smoke from the wildfire season in the summer. And not only in the Arctic, But also in Greenland and Antarctica, other campaigns such as Operation Icebridge studied the impact of emissions on these regions, as well as the behavior of the rapidly changing features of the Arctic and Antarctic ice sheets, ice shelves, and sea ice.
My first mission with the DC-8 was Operation Icebridge, where we spent several weeks flying down to Antarctica. And it's undescribably beautiful.
I've been flying on the DC-8 between 2011 to 2024. I've been involved in the Operation Icebridge, flying over the Antarctica, doing ice studies on the Weddell Sea, the Pine Island glaciers.
Operation Icebridge became the largest airborne survey of Earth's polar ice ever flown. It also helped to fill the data gap in polar observations between the retirement of NASA's IceSat satellite in 2009 and the launch of the new IceSat-2 satellite in 2018.
I've also been on the FireX campaigns, operating out of Salina, Kansas, and studying the smoke pollution into the atmosphere. Also worked on Seekers, which was a cloud experiment in Houston, Texas. We would fly all over Houston area, also into Louisiana, and also up to Arkansas.
So the DC-8 was also kept busy flying campaigns over the continental US, tracking air pollution, fires, and even flying into the eye of a hurricane during the GRIP campaign. But also flying around the world with ATOM, a multi-year campaign that covered vast areas of the Pacific and Atlantic Oceans from north to south and back.
We left from Palmdale, went to Alaska, from Alaska to Hawaii, Hawaii to Fiji, Fiji to New Zealand, New Zealand to Punta Arenas, Chile, down to Antarctica, then up to the Atlantic side on Ascension Island, and then lodges in the Azores, up to Greenland, then over the Arctic, back to home.
Other missions have also required the aircraft to operate far away from home, like in Korea with Chorus AQ, a campaign that would lay the groundwork for a new way of integrating multiple data sets from different sources to create the most accurate picture of air pollution ever recorded. There's no doubt that the aircraft has flown its fair share of miles in campaigns around the world, and it's been a useful platform for atmospheric studies. But it's only in the last decade that we've been able to integrate large data sets from different sources to focus on very specific areas.
A big part of what we do with integration of vantage points, it's not just airborne science, but it's the integration of satellite measurements, airborne measurements, and surface measurements, as well as in collecting all the data, utilizing Earth system models to integrate it, produce hybrid model observation products.
But it's only in the last decade that we have finally begun to focus on urban areas, polluted areas, areas where there's a ground network that we need to tie ourselves to. And so this relationship between space, the ground, and the aircraft has really come to the forefront in this last 10 years, and how modeling can really benefit from that.
You know, it's all an integrated piece in terms of utilizing these different vantage points to improve our knowledge about the Earth.
Over the past decade, the integration of data from satellites, ground stations, and aircraft has helped improve our measurements and understanding of important issues such as air pollution. In the summer of 2023, during the Stock's Aroma campaign, the DC-8 flew out of Dayton, Ohio, hometown of the Wright brothers, on a mission to validate this proof of concept.
So we have air at the ground that we're measuring, but we can't have monitors everywhere. The other side of the spectrum is we have a satellite up at 22,000 miles away, and it can close the gaps between those monitors and understand how that pollution moves and evolves throughout the day. And then we also have airplanes that will go out for a small period of time and measure at higher spatial resolution.
So NASA and NOAA in partnership are going to fly the DC-8 to get vertical and horizontal distribution near the surface of the gases that TEMPO measures, which is nitrogen dioxide, formaldehyde, SO2, as well as some information about ozone.
In this field campaign, the DC-8 G3 and G5 took measurements over New York, Chicago, and Los Angeles to help calibrate the TEMPO satellite.
So we have the TEMPO satellite that's up above our head, and we're stacking it with airplanes that are in the middle, giving us information about the vertical distribution of pollution, as well as measuring different gases that we're not measuring from a satellite, and connecting it to the surface, where we're measuring surface air pollution, and the air that we're actually breathing in is relevant to our air quality.
We'll get some really valuable data to do science understanding air quality in the 3 largest cities in the United States, as well as data to help us test out how well is TEMPO really working.
By integrating data from the ground, aircraft, and satellites, we can get a detailed picture of air quality not only at the time of emission, but also as it evolves throughout the day, which is critical to accurately predicting pollution and the health effects on the population. Which brings us back to the DC-8's final mission.
And then on the way back, we'll do a little bit of profiling. So we'll play that by ear as we go. So at NASA, our commitment is to understand the Earth, the global perspective. And so we are paying attention to what's happening across the world. We're also cooperating with our international neighbors to take better and better observations. And for air quality, we've determined that geostationary observations are critical, because as things evolve throughout the day, it's important to understand what's happening.
Just as the TEMPO satellite is over North America, the GEMS satellite is collecting data over Southeast Asia. So the same kind of airborne campaign as Stock's Aroma would be very helpful in this other part of the world.
So AGAQ is the Airborne and Satellite Investigation of Asian Air Quality, and we are hoping to do that in 3 cities in Asia.
There's a lot more development in Asia, and there's a lot more diversity in Asia. GEMS is looking at many different countries with many different cultures, many different economies, many different meteorologies. And so from a scientific perspective, exploring those differences and that range of possibilities is very, very valuable, especially in areas that are developing and experiencing some of the worst air quality that comes with those growing pains of developing strong economies, but also trying to control the impacts of that.
So in February and March 2024, NASA and its international partners launched an airborne campaign that would benefit 4 countries in Southeast Asia, including Korea, the Philippines, Thailand, and Taiwan.
So AGAQ is not just the US NASA, but also the Koreans working with the US, going to these other countries and saying, we think that there's an opportunity here for you to learn with us how to make better decisions about your air quality policies.
International collaboration is the key to understanding the Earth as a system, and something that will benefit all of us who live on the planet. But, as you can imagine, getting these aircraft, instruments, and scientists to different missions around the world is no easy task, and there are always unexpected problems that can jeopardize the mission. In fact, the DC-8's final mission was almost canceled during the Korean deployment.
Now, I don't know if you saw in Korea what had happened with having to have that engine change. These guys may have changed engines on a 747, but they have never changed an engine on this.
During AGAQ, a faulty engine put the entire mission at risk.
You know, we're on the ramp. We're looking at, with wind chill, maybe teens, air temperature, trying to get this changed on a ramp in Korea. And they did it just a little bit longer than what we would have did at home in a hangar, being comfortable. Wednesday, when they first started the engine, everything just went through seamlessly. It was a relief.
Thanks to the mechanics, crew, and aircraft managers, they solved the problem, replaced the engine, and completed the mission successfully.
So hats off to the mechanics who pulled it off, and they did a very good job. And I was really impressed. Again, don't tell them that. Swelled heads will never get them through another doorway at an aircraft.
And runway heading climb 4,000, runway 0 clear for takeoff.
NASA817 copies, runway heading to 4,000 and clear for takeoff from research.
So at the end of the day, it's the team, all the people involved in the campaign, that make a mission successful. But it also takes a lot of coordination and planning ahead.
We start out a couple months ahead of the science campaign itself, working with the researchers as far as where they want to gather data. We learn what air traffic control environment they want to gather data in, and we start coordinating with air traffic controllers. We get the waypoints that they want to go to from point A to point B on a particular line or a overfly of a point. We'll use that information to get permissions from air traffic control to do that type of work. So we get all those permissions laying down up front before we try and get in the field. So it takes a long time and a lot of back and forth.
In the meantime, all the instruments must be installed and tested on the aircraft. And not just the instruments and the flight plan, but also the logistics involved in carrying out operations of this magnitude.
We need people, not just people to fly and maintain the planes and the instruments, but people to figure out how do you bring, in some cases, 100, 150 scientists into the field, working in a variety of conditions, not necessarily the best. Some may be very remote, maybe harsh environment.
As a matter of fact, NASA has a group that focuses on this very task.
NASA's Earth Science Project Office, ESPO for short, specializes in the large multi-aircraft international campaigns for NASA headquarters.
ESPO is involved in all phases of the mission, from its conception to its planning and the implementation. All the planning starts about 1.5 years, 2 years out, where we come and do a feasibility assessment of the deployment areas. We need to understand what the researchers want, which become our requirements, and then we come here and see how we can best meet those requirements, whether they are logistical or operational.
We have to make sure that they have the ground support equipment and facilities that can support the aircraft, but also labs and offices for the scientists to be able to use.
You have to have fuel, you have to have internet, you may need liquid nitrogen, you got to have supplies, and if you've got people, that means you need hotels and rental cars and medical care, and you got to figure out how to operate safely. So you have the people to do all that. So it's not just the scientists, it's everybody it takes to make it work.
So, yeah, NASA campaigns are quite a complex endeavor. And only when all the elements are in place and the right people are involved can a mission be successful and valuable data be collected. But why is it so important to study our atmosphere?
Being able to make reliable predictions is important, and it's important because weather matters.
Farmers need to know what kind of crops to plant. It depends on the temperature, it depends on the amount of water, and if we can give them a better idea of where those things are going, they can improve crop yields, for example.
It matters to disaster relief people. You know, is there going to be a big hurricane, and can we predict where it's going to make landfall? Can we predict how strong the winds are going to be?
Actually, a colleague of mine has done a study onto the social value of the cost of Earth observations. And he just did it for one particular observation, where having this information can give stakeholders the information they need in order to better make decisions. And they've converted that into actually how much you could save by making the right decisions earlier. And when they did this calculation, they calculated many billions of dollars in kind of payback that you get by having this information sooner rather than later.
Many, many reasons for knowing how weather's going to be. And the kind of data we produce will improve weather models.
Understanding our planet is one of NASA's primary goals. That's why collecting and analyzing data is so important.
So scientists, we want to understand the atmosphere. We want to understand the atmosphere so we can better project where it's going.
It's having the information. So it's knowing the choices that we make and what impact that has on society in the long run. And to me, that's what we're working for.
And this is critical to understand humans' impact on the planet. And with that information, we can hope that we give the public and the policymakers the best information so they can make informed decisions.
And the DC-8 has certainly been helpful in this regard by providing the necessary opportunities for the collection of such valuable information.
So to be able to be the last group to use the DC-8 is both bittersweet but also very gratifying. This platform has enabled us to do things that would be impossible otherwise, which is both to measure the atmosphere in great detail, but also show others what we do, to have guests on board, both to observe and to measure. We have 8 instruments on this plane that are not NASA or NASA-sponsored instruments, and that means that we're growing airborne capacity around the world.
Every nation, it's very much connected, right? This is a thing about the atmosphere is, you know, things do not respect state lines or country lines. It's just the whole globe is really connected by the winds that are blowing.
So I really look forward to a day when many other groups, not just NASA, are making these measurements around Asia and Africa, South America, and wherever in the world we need them.
Asia AQ was the last science campaign for the NASA DC-8. However, the platform was not only used for research, but also to inspire the next generation of scientists.
One of the things that's really neat about airborne science at NASA is that if you look at the people who are on the planes, a lot of times it's early career investigators, it's graduate students, it's postdocs, it's people who have their first jobs, because what it means is that they can build the instrument, they can fly it, they can collect the data, they can analyze the data, and do all of those things. So we provide educational opportunities too. Every year, for close to 15 years now, we've been doing a student airborne research program where we bring about 30 students from around the country, mostly rising seniors who participate in our airborne science program.
We're in Southern California. We have our airplanes fully integrated with our instruments, and we're testing out our payloads and testing out some of the flight plans that we're doing, while also contributing to a really cool internship program that I can probably attribute my career to, as I was a student back about a decade ago in this program. It's the NASA Student Airborne Research Program, and it gives students hands-on experience in doing airborne science and seeing what NASA does with respect to airborne science and earth science in general.
They fly on the planes, they help collect data, they analyze the data. The airborne science provides a great way for people to really, get their hands on the instruments and take things from end to end. So build the instrument, fly the instrument, collect the data, write it up, and then also begin to understand the relationship between what we do in the air and what we do from space, because integrating vantage points is really important to us. And many of the people who sort of start out doing airborne science end up being the people who do the satellite missions for us. So it's it's an important part of our overall program.
I think a program like SARP is really important for engaging young scientists because it shows them a side of NASA that people don't typically think of when they think of NASA as itself. They think we're going to the moon, we're studying space, but we're really interested in understanding the planet that we live on, Earth. And so it's a cool opportunity for students to come out and learn that side of this. Not everybody is an Earth scientist when they started, but some of them decided to pursue careers in that direction because they were inspired to study the ocean or land biology or air quality.
So that their first real research experience in Earth science may be doing airborne science. It's they have a blast, they learn a lot, and they have successful careers.
Airborne science, student engagement, and cutting-edge research. NASA DC-8 has helped us explore the Earth over the years, gathering valuable information about our atmosphere and the processes that directly affect us down here on the surface.
The DC-8's got a marvelous legacy. We've been using it for a long time. It's a really important platform when you think about all the places that it's been, so many places that we've been able to go to conduct studies over the years. You know, all the people who had the privilege and who invested their heart and soul and energy into making those campaigns productive.
I have been assigned to this aircraft for almost 10 years. And it's been just an amazing experience. The places I've seen, the people I've met throughout the world, it's just been a phenomenal experience.
So my first outing with the DC-8 was as a graduate student at Georgia Tech. That was 1994, and it was actually in March, which means that we're maybe not to the day, but to the month. It's exactly 30 years since my first ride on the DC-8. So a lot has changed over that time.
After this science campaign is over, I should be at 168 flights on the DC-8, which would equal to, currently it's going to rise, but right now I'm at 1,216 flight hours on the DC-8.
I've flown on the DC-8 4 times myself. I think it was like maybe 1989 and the first airborne stratospheric expedition out of Stavanger, Norway. And I've flown on it 3 times since in Costa Rica, in Kansas, and in Cabo Verde.
I put a lot of blood, sweat, and tears in this thing, literally.
Just being on the crew of the DC-8 is a rewarding experience. I always say to everybody I know, if you love your job, you never work a day in your life. And so I really, really love my job.
So it's gonna be heartbreaking. I keep it real. I mean, you grow attached to something when you spend so much time on it. So
NASA 817 returned home after its final campaign in April 2024 and was retired after 128 science campaigns and 37 years of service.
I mean, I think the important thing is one looks back over the decades of use of the DC-8 and all the things that we've accomplished scientifically and all the careers that we've inspired and enabled. And, so I think, we don't look at this so much as the end of an era, but it's really the successful conclusion of one phase as we transition into the next one. Everything that we learned and did on the DC-8 we'll be able to bring with us and transition as we move forward.
And actually, NASA has already acquired another aircraft to continue the legacy of the DC-8.
So we're now the proud owners of a Boeing 777, which, talk about the DC-8 being big. 777's much bigger. It's got a range probably for up to 18 hours. So there's a lot of capability that's going to add to our fleet. But we have to put the holes in the bottom for remote sensing, put the holes in the side for inlets for in situ instruments, provide all the kind of wiring and things that we need to be able to get the instruments talking to each other and getting data and do all the communication stuff. So a lot of work that we need to do before we have that as a platform. So.
And when ready, scientists will have a new and improved tool to conduct the vital atmospheric research that benefits us all. But the DC-8 will always have a place in the hearts of all the people who worked on it and eventually became part of the NASA817 family.
So I've been taking chronological pictures of all my flights and then making like a digital virtual scrapbook, right, of all the missions I've been on, all the places we've been to, right? And also the people that were involved in that mission at that particular time. All the different scientists that might have been there, and also all the different passengers that we had, so that when I move into the retirement phase, I would be able to look back fondly on the memories and all the good times that I had while operating on the DC-8.
I was explaining this to my wife, and I spend more time with my group than I do at home. So the way I explained it to her is, this is my family.
Because it's the people and the crews that make the DC-8. And the DC-8 is definitely the best, bar none, crew there is. So always happy to be with the best.